Welcome to our presentation on controlling prosthetic grip strength with the NeuroSky. My name is Guillermo Rios, and I'm the first member of our group. We were interested in designing a neuroprosthetic device that restores the grasp function for people with spinal cord injuries. With the help of Trident Prosthetics, a club at UCSD aimed at providing low-cost prosthetics to the community while improving prosthetic design, we use the NeuroSky to read EEG signals to control the grip strength of a 3D printed prosthetic. Our project can be briefly summarized as reading attention EEG signals from the user via the NeuroSky, which then send those signals to the receiving computer. This computer is connected to an Arduino board, which is connected to a motor that controls the prosthetic. Despite being a prototype, we believe this project has the potential to branch out to a real-world application for amputees and people with limb differences. Prosthetics are currently relatively expensive, so another goal we had in mind was creating a low-cost prosthetic that has similar capabilities as the higher-cost models. We used the BCI review paper as a guideline for our project. Since we're all new to BCI applications, this paper was incredibly useful in the development of our project. The BCI review paper linked us to an article called Control of an Electrical Prosthesis with an SSVEP-based BCI. This is how we decided to follow through with this idea. In the developing phase of our project, we found 2 additional articles that were relevant to prosthetic control through the use of EEG-based brain-computer interface. There was a common use of motors controlled by some type of input, mostly EEG data, to move the prosthetic. This method is very similar to how we controlled the movement of our prosthetic. These articles use different methods, including an adaptive autoregression model, steady-state visual evoked potentials, and haptic feedback to control a prosthetic. We decided to use a moving average to smooth the input data, but we still took into consideration these other models for future implementations of our project.
Hi, my name is Nathan, and for the data collection, we used the NeuroSky with Python to collect the values. And we used the Mindwave Python parser to interact with the NeuroSky because that was the only library we could use with the Mac. And we used that to collect both attention and meditation readings. And then connecting the NeuroSky was relatively simple because instead of a Mindwave, we used the Mindwave mobile headset so that some functions that in the sample code or examples were actually not needed, such as the connect function. And we used the library to collect and store attention and meditation values read by the NeuroSky by the participant. And initially we tried using the blink value, but eventually we found out that it wasn't very reliable. And there were some functions that would also not work, such as printing the current status of the headset, like whether it was connected or not. So we decided not to use those either, just for like error checking. And after looking around with the attention and meditation values and seeing what would work or not with the implementation, we found that the meditation value was not exactly what we were looking for and did not be good enough for the hand to move. So we just used the attention value to record data and that we would then send to the Arduino.
My name is Angela, and I'll be talking about the smoothing portion of our data processing. After playing around with the NeuroSky for a bit, we noticed the attention values were pretty susceptible to sharp increases or decreases, since it was only measured once every second. We decided to implement a smoothing method in real time on the data so that the hand wouldn't be opening and closing abruptly. I'll first talk about the methods we used, and the next slide will go into some of the options that we didn't end up using. So we actually ended up using a pretty simple method for smoothing, which is a moving average with a window size of 5. Basically, for every new attention signal that was read in, we would average the most recent 5 values and output that to the hand. We decided to compare the difference between using a normal average, which was just the sum of the 5 values divided by 5, and a weighted average where more recent values were weighted heavier. We gave the oldest 2 values a weight of 1, the middle value a weight of 2, and the most recent 2 values a weight of 3. The outputted averages were then stored in the array, which was written to the Arduino. For our final demo video, we ended up using the weighted average because it ended up having a smoother grip. Now here's some methods we didn't end up using but thought were interesting. Our first idea was to use some sort of regression method to smooth out the data points. We found 2 methods that seemed promising. The first was locally estimated scatterplot smoothing, and the second was locally weighted scatterplot smoothing. They're both local regression methods, which are a generalization of a moving average and polynomial regression. However, after looking into it further, we realized this would be difficult to use since we needed the data smoothed in real time, and these are scatterplot smoothing methods where all the data is there already. We also looked into a smoothing method for signal processing from SciPy documentation, which involved using numpy.convolve in various types of windows. However, it seemed unnecessary for us to use since we were using the attention values from the NeuroSky and not raw data.
Hey, it's Mark, here to talk about the Arduino and motor actuation of the prosthetic. We used an Arduino Uno to control a linear servo motor attached to the actuators of our prosthetic hand. The Arduino code consisted of reading in the values from the computer and writing them to the serial port of the Arduino. A 15 millisecond delay was used to allow for the motor to reach the values. Important to note, no scaling was performed to translate the filtered NeuroSky values to the motor, simply because the NeuroSky values ranged from 0 to 100, as did our decided range for the motor. To actuate the prosthetic hand, we used a linear servo motor to control a Whipple tree attached to the fingers of the prosthetic, which allows for independent movement of the fingers, as opposed to the movement of one finger being limited by the movement of the others. We also decided to attach an external power source to the motor to increase power, since the max output of the Arduino is 5 volts, a value we deemed to be too weak to properly actuate the prosthetic hand.
Hello, my name is Sahil Patel, and I will be covering results. What did we discover? We discovered a lot about the problem we tasked ourselves with. First of which were the mechanical constraints of the problem. Our arm requires very high-end materials and very good motors for it to work at a practical application, such as picking up objects and doing various other things that someone would want to do with their hands. Software-wise, there wasn't a lot of issue. We were able to get meaningful data from the NeuroSky, and we were able to communicate our software properly with the Arduino, which was able to send the motor commands to move the arm and close it and open it, essentially. Did it work? Our NeuroSky was able to return values that were normalized. It was able to smooth out the values that we obtained, which ensured that our arm wouldn't have sporadic behavior and it wouldn't jerk back and forth. The motor moved properly based on the value of attention, but this came with problems. Because of our material, as mentioned before, our materials would bad. The servo would get stuck due to friction, and our motor was not strong enough to pull said servo, so it wasn't closing all the way when it should have. In the end, however, with all of this, we discovered a way of converting EEG signals of attention and using it to control a mechanical device. So in a sense, the conceptual task was accomplished. However, we can't necessarily say if this was a step forward in the world of neuroprosthetics. As you can see in this video, Mark will attempt to control the arm using NeuroSky, and you can tell that the more he focuses, the hand will close, but at a certain point, the servo gets stuck and the motor can't pull it past that threshold. All we have to do is turn in the video, right?
Look, now oh, there we go.
This one. I don't know, see, I can use.
All right, what's up, guys? My name is Nicholas, and today I'll be talking about the discussion. So first, I want to address what we learned. We had to learn how to communicate to the prosthetic. So for some of us who weren't familiar with the Arduino, we had to familiarize ourselves with it, as well as the Arduino software. Also, we had to familiarize ourselves with the MindWave setup, and that would allow us to connect and interact with the NeuroSky to essentially obtain its readings via Bluetooth. And then lastly, we had to connect the last piece of the puzzle, which was to combine our prior coding knowledge with some research of the readings from the NeuroSky and reduce the noise to produce gradual results to send into the Arduino. And this would essentially move the prosthetic and give us a more gradual result in reducing the noise. Next, I want to address what we can do better and maybe a follow-up development. I'm also going to combine this section with the two extensions or improvements with justification, basically our two major issues. So one, we always want a better way to reduce the noise and make these imported values more gradual. When we were using the NeuroSky, we were getting readings that were very high and very low, and a lot of the times it was unexpected. And our value had much noise and fluctuation pretty drastically, which would cause the hand to essentially like spaz out, and that's something we didn't want to do, and it wouldn't be optimal because it wouldn't show that we can actually control it. Another approach to this would maybe to implement our meditation values. When we were using the NeuroSky, we had our attention values and our meditation values. However, only the attention values were being used, and also these two values were independent of each other. So maybe we could find a way how to incorporate the meditation values and the attention values to maybe smooth out a better curve, which would lead to more gradual results. And this way, if our meditation values were high, we can control our attention values and vice versa. But that also brought up the question of what is the meditation value? Does meditation mean resting? And intuitively, we would think that it takes focus to meditate. So to kind of discover how they're dependent of each other and how they are correlated. But that's a whole nother issue we would have to do. So for our two extensions or improvements, our two major issues, one, I want to explain about the hardware that we had. This was probably the most limiting factor that we had, which was the plastic that we had. We found that even though our tension values may have been high at some points, our rail and motor was not strong enough to actually close the hand fully, and it was only able to partially close the hand, which would limit our range of motion. And also it was kind of weird because you would hear the motor kind of spaz out, but the hand wouldn't fully close. We would definitely have to use something more sturdy and with something less friction. And my guess would be something more light and strong, and probably a metal such as aluminum, which has probably like that rail lubricated so that the motor would work directly with that and control the linear servo with ease, basically. So that would be a smooth operation. We could also probably add more better material to pull the fingers. We were using like this flimsy kind of weak rope, almost like yarn. It was very weak, and so we would probably want to substitute that with something such as like fishing lines or something strong and sturdy, but with a little bit of elasticity. And also always to make the model more compact for comfortability and to reduce the feel and look of it being a prosthetic, more realistic, so that it does increase the popularity of our product. And the second limiting factor, or major issue, would be our software. And most of the time we experienced, like I said, like unexpected results for the attention values being very high or very low. So sometimes when we try to pay more attention, the values wouldn't jump high and it might have dropped or might have stayed the same. And vice versa, sometimes we try to unfocus and our attention values will actually jump. So this meant we should probably have something more in control and something more reliable when it comes to measuring our focus. So I remember talking to one of the TAs about this, and an alternative would be to try different BCIs to get more control of our outputted values, such as like an open BCI or EEG booster, which contains more channels. I think it was like 8 to 12, which ultimately led to more functionality, which would have just better readings. Moreover, to continue this idea, we can receive more accurate readings if we use an invasive BCI, which would essentially mimic our brain better. But overall, our group had a consensus that EEG readings might not have been the best route to take for this project, and that the most optimal solution might be to read muscular signals, since this would give us more control, which yields better readings, more predictable results. That's kind of more of a natural feel. So that concludes our project. We want to thank you for your time and attention.